Hello, my name is Jonathan, and in this video we will be deriving Maxwell's wave equation, and this will be done using some of Maxwell's equations such as Faraday's law, the Ampere-Maxwell law, and Gauss's law. This derivation can be performed with respect to the electric field or with respect to the magnetic field, as these both make up an electromagnetic wave. Before performing this derivation, we must envision the system that we are deriving the wave equation for. First, we must assume that the wave that we are deriving for is traveling along a given axis and that the wave is linearly polarized. So if we have an x and y coordinate system, this wave is traveling in the x direction and oscillating in the y, and it does not change the direction with which it oscillates. So in other words, this can fit within the plane of a board or is a plane wave. In addition to this, we must assume that the space with which we are deriving, or I guess another way to say it, the space with which the wave travels, is free of any sources. So there are no charges, there's no electric fields, etc. Finally, we must assume that we are in Euclidean space, and that'll be useful for some transformations we'll make in our derivation later on. So, as you can see here, I have a few identities that will also be useful to us, as well as some that may not be useful to us. In this derivation, the main identities that we will be taking into account will be the curl, as well as the curl of a curl. We can now begin our derivation with respect to the electric field, which we'll go ahead and indicate, and we'll do that by starting with Faraday's law, which reads, del operator cross vector field E is equal to the negative derivative of the magnetic field with respect to time. From here, to continue the derivation, we must take the curl of both sides of the equation. Taking the curl affords us the following: del cross vector field E is equal to del cross quantity negative derivative of the magnetic field with respect to time. And here, there is now an equation at play. So if we go ahead and look at the left-hand side of the equation and scroll up a little bit to see the curl of a curl identity, we can see that del cross psi is equal to del dot psi minus del squared times psi. And that can then be applied to our left-hand side of the equation, affording us the following: del dot E minus del squared times E. And that's equal to the same thing on the right-hand side of the equation, del cross the negative derivative of the magnetic field with respect to time. And once again, there's another substitution that we can make. However, this time, it is no longer an identity, but rather one of Maxwell's equations. More specifically, it is Gauss's law of electricity, which reads, del dot E is equal to rho, which is charge density, over epsilon naught, which is the vacuum permeativity constant. So subbing in rho over epsilon naught, we can afford the following: del dot quantity rho over epsilon naught minus del squared E, del squared E, which is equal to the right-hand side of the equation, which is del cross quantity, the negative derivative of the magnetic field with respect to time. Now from here, we can go ahead and do some rearrangement of the equation. So what that will entail is we will first be taking epsilon naught out of the del operator equation on the left, and then on the right side, because we're in Euclidean space, we're going to be able to switch this del operator with the derivative with respect to time. So going ahead and doing that will afford us the following, and we'll scroll down to go ahead and write this new equation. This new equation will become 1 over epsilon naught times the del operator dot charge density rho minus del squared E, and that's going to be equal to the right-hand side of the equation, which is now the negative derivative with respect to time times del cross vector field B. Now another substitution that we can now make, once again based on one of Maxwell's equations, more specifically the Ampere-Maxwell law, which reads as follows: del cross B is equal to mu, the permeativity of free space, times J, the current density, plus epsilon naught, the permeativity of vacuum, times the derivative of the electric field with respect to time. and those are parentheses just to be clear. So now subbing in the right-hand side of the equation for the quantity in parentheses here, we can afford the following. So scrolling down to give us a little bit more room, we can obtain 1 over epsilon naught del dot rho minus del squared E, and that's equal to the negative derivative with respect to time of the quantity of mu naught times quantity J, current density, plus epsilon naught times the derivative of the electric field with respect to time. Now from here, recalling that we are in a source-free space with no charges at all that can interact with our wave, we can go ahead and set two things equal to 0. More specifically, we can set the charge density to 0 because, again, there are no charges, therefore there is no charge density. And we also have no current density J because there is no current, and that is also because there are no charges. So, because of such, this equation simplifies like so, and we'll go ahead and write the new form of the equation below. Del squared E is equal to the negative derivative with respect to time times the quantity of mu naught epsilon naught and the derivative of the electric field with respect to time. Now from here we could go ahead and bring the derivative into the brackets on the right hand side, and that will afford us the following: mu naught times epsilon naught times the quantity of negative derivative of the electric field squared over dt squared. And then on the left hand side we just have minus del squared E. Now here we can go ahead and realize that we have a negative sign on both sides. Multiplying through by -1 affords us positive on all ends. And then from here we can go ahead and expand, if we're only in one dimension, this del operator on the left hand side. If we're only in the one dimension, and we'll call that the x dimension, we will have the following. We will have d squared E over dx squared, and then that's equal to the right hand side of the equation, which is mu naught epsilon naught times d squared E with respect to time. And this is almost the final wave equation, but there's one more substitution we can make, and it's helpful to know that velocity is equal to 1 over the square root of mu naught epsilon naught. So if I have mu naught times epsilon naught, that would be the same thing as squaring the right hand side of the equation, and if I square the right hand side I have to square the left hand side. Therefore, if I have mu naught times epsilon naught, that's now equal to 1 over v squared. So going ahead and making that substitution, we now have our final form of Maxwell's wave equation with respect to the electric field, which becomes the derivative with respect, the double derivative with respect to position of the electric field, and that's equal to 1 over v squared times the double derivative of the electric field with respect to time. So there we go. We have now derived Maxwell's wave equation using some of Maxwell's equations with respect to the electric field. You will see now, from the perspective of the magnetic field, we will get the exact same result, where instead of the double derivative of the electric field, it will then be the magnetic field with respect to position, and in that case x, and on this side it will also be the magnetic field with respect to time. So going ahead and starting that derivation to see this, we are now doing this for the magnetic field, so we'll indicate that. And this derivation begins with the Ampere-Maxwell law, which reads del cross vector field B is equal to mu naught times the quantity of J, which is current density, plus epsilon naught times the derivative of the electric field with respect to time. And that's a little messy, so apologies for that. But from here, we can again continue the derivation by taking the curl of both sides, which affords us the following: del cross B, which is equal to del cross quantity mu naught times the quantity J plus epsilon naught times the derivative of the electric field with respect to time. Now from here, once again, we can use the curl of a curl identity, but this time with respect to the magnetic field B, and that affords us the following: del dot B minus del squared B is equal to del cross quantity of mu naught times the current density J plus epsilon naught times the derivative of the electric field with respect to time. And we'll close our brackets here. Now from here, instead of subbing in Gauss's law of electricity as we were able to do before, we now have a different Maxwell equation equivalence shown here, where the del dot B is actually del dot B, which is equal to 0. Therefore, this entire term will go to 0, and we are then left, not sure why my writing keeps disappearing, but we will then be left with the following. So scrolling down and filling in what that would become, that's now going to be minus del squared B is equal to del cross quantity mu naught times J plus epsilon naught times the derivative of the electric field with respect to time. Okay, so now that we're here, we can then make another rearrangement similar to what we had done before, but only on the right hand side this time. We're going to take this del operator and switch it with the derivative with respect to time. And that will look like so. Oops, sorry about that. So we have the minus del squared B is equal to the negative derivative with respect to time times the quantity of mu naught times the quantity J plus epsilon naught times del cross E. And we can go ahead and put that in a set of parentheses. We'll close this set of parentheses, and then finally the brackets. Now from here, del cross E should look familiar to you guys, because that is the exact same thing that we had to start the other derivation with respect to the electric field. So del cross E is actually Faraday's law, and we can go ahead and substitute in the equivalences for Faraday's law within these brackets. And that's going to then become, on the right-hand side, the negative derivative with respect to time times the quantity of mu naught times the quantity of J plus epsilon naught times the quantity of the derivative, and more specifically the negative derivative, of the magnetic field with respect to time. I'm closing all our brackets and then filling in the left-hand side of the equation. This is now our form of the equation we're using. Okay, so from here, there's a few things we can now take notice of. Once again, we do not have any charges, and there is nothing that can interact with this electric field propagating in space. Therefore, current density J will once again go to 0. When current density goes to 0, you will see how this equation can transform into an extremely similar looking equation to the previous one we just derived. So that will then afford us, that'll afford us negative del squared B, and that's equal to, now on the right hand side, we have mu naught times epsilon naught times the quantity of the negative double derivative of the magnetic field with respect to time. From here, we're almost done. We can realize that there's a negative sign on both sides, so multiply through by -1 to make those positive, and we could then make the substitution for mu naught times epsilon naught. And going ahead and performing that, as well as realizing that we are doing this once again for one dimension, we are afforded the following. The double derivative of the magnetic field with respect to position, and in this case x, is equal to 1 over velocity squared times the double derivative of the magnetic field with respect to time. And thus, we have now derived the Maxwell's wave equation from the perspective of the magnetic field as well as with respect to the electric field.